If you're a cyclist, you know how important it is to stay visible on the road, especially in high traffic areas. Cyclists are often put in precarious positions, especially if they aren't taking any safety precautions. Based on a 2020 survey, preventable cycling deaths capped at over 150 per month. Professional cyclists are no stranger to the dangers of cycling either. A simple wheel touch is all it takes to bring the peloton down, causing countless injuries. Here we show a crash from the 2022 cycling race Tour de France. That being said, for our embedded AI class project, we chose to implement a smart bicycle brake light to combat some of the issues regarding safety that cyclists face. The idea is simple. We want the taillight to flash or go into strobe mode when the cyclist is braking and stay solid when the cyclist is coasting or accelerating. We do this by capturing the last 1 to 3 seconds of accelerometer data and making real-time inferences every 25 milliseconds as to whether the system thinks the cyclist is braking or not. In our market research, we saw that brake adaptive taillights do exist. This one from CME has been regarded as one of the best in the market. However, it has a couple of disadvantages. First of all, the price is very expensive. This one is listed at $80, whereas our preliminary guess to mass produce our light is around $30. Second of all, the light uses a thresholded method to make decisions on the braking state. This method has additional disadvantages. To name a few, it is very susceptible to noise, which makes it very prone to false positives and misclassifications. With that being said, let's talk about the process of data collection. So we finished up our data collection for today here in Riverside Park. The main reason we came out here is because of the wide array of road surfaces. You can see we have a lot of rough road surfaces, some dirt, as well as this smooth road surface.
In order to combat environmental noise, we run our raw data through a common filter, which uses a combination of next-step prediction and measurement-based correction to reduce the effects of noise. It's not an expensive computation, and based on our testing, a well-tuned common filter gives drastically better results than using raw data.
This is then fed into a one-dimensional feature extractor. By using a convolutional layer with kernel shape of 4, we get the features from the data that are consistent with the context of the collection. We then input the features into an MLP and get out a binary classifier of whether the cyclist is braking or not. Thanks to TinyML, the total model size is about 1 megabyte, which fits onto the Arduino and performs inference in less than 25 milliseconds. Now let's go into the results of our completed prototype.
All right, here we go. Heavy brake.
Here we show a couple of prototype testing demonstrations. In the graphs you see, we compare gram truth values to real-time inference by the embedded AI model.
Stop.
But we'll see how it goes.
All right. Go ahead.
Okay. We've proven that the model successfully generalizes to data given the different scenarios we tested and trained in, and given the very high confidence scores and the footage that we showed you previously, it should be working well. With all this in mind, thank you for your time, and let us know if you have any questions.